This is Chapter 8 on sampling distributions, and so we're going to learn the difference between having population data and sample data. So what we have here is a list of all of my students' averages over the past 3 semesters. So there's 300 averages here in this chart. And what I have my face-to-face classes do is pick samples of size 10 and come up with a sample mean. And then they do it again and again and again. And they keep picking random samples of size 10 and coming up with sample averages. I know that the population mean of all 300 of these scores is 74.6, and the standard deviation of all 300 scores is 13.8. But if I were to take 50 samples of size 10 from this population, what kind of sample averages would I have compared to the population mean? So if we know the population mean is 74.6, sample averages would probably be in the 60s, maybe 65, 68. There'll be several in the 70s. 73, there might be a few 74s. 75, there could be a few that are bigger. Sometimes I have students who get averages in the 80s. But they'll all hover around 74.6. The majority of the sample averages will be somewhere around that 74.6. And if we took all 50, I know I don't have 50 here, but let's pretend like we have 50. If I made a histogram of those 50 sample means, what kind of standard deviation would it have compared to the population? So the population has a relatively large standard deviation. These scores are relatively pretty spread out. You'll see some hundreds in there. I also have some 50s in there. So it's pretty spread out. But with the sample means, they're all going to be hovering pretty close to 74.6. There might be a few low and a few high, but the majority of the data is going to be right around 74.6. So generally speaking, it's going to have a smaller spread than the population, because we're not going to have so many extreme measures to factor in. So like I said, when I do this with my face-to-face class, we actually plot all of these sample means onto a dot plot, which makes kind of a rough histogram. And that histogram spread is much smaller than the population spread. And that's because, again, most of the sample averages are going to hover around at 74.6. So there's some conclusions to be made from working with samples. The first one is that the shape of a sample distribution is approximately normal. Remember, normal means bell-shaped. So Chapter 8 is an extension of Chapter 7. So everything that was true in Chapter 7 is still true in Chapter 8. The center of a sample distribution is the sample mean, which is generally pretty close to equal to the population mean. Again, it's not going to be exact, but it's going to be close to that 74.6. And finally, the spread of a sample distribution is called the sample standard deviation, which will be smaller than the population standard deviation. Remember, this is accounting for 300 scores, so it's going to have a much bigger spread than just little samples of size 10. So the center is about the same, and the standard deviation is going to be smaller. So that's what we're looking at in Chapter 8. How does the population parameters compare to sample statistics? Alright, so the average of the means of all possible samples of a particular size. So if I take all the sample means and average them all together, we call that the mean of X bar, which is the mean of every single possible sample of that particular size. And if I were to average all the samples together, it would equal the true mean. So the mean of all the samples of that size, put them all together and you get the true mean. The standard deviation of, again, all possible samples of a particular size from a population is sigma of X bar, which is the true standard deviation divided by the square root of the sample size. That's something you'll need to know to make that adjustment. Both of those, where are they? Both of those calculations are here. I'm at the top of page 3 in the Chapter 8 formulas. So you'll see the mu of the x bars equals mu, and the standard deviation of the x bars equals sigma over square root n. So it's very important to remember that the standard deviation gets adjusted. Standard deviation in this unit is also going to start to be called the standard error of the mean. You might start to hear that as we get into chapter 9 and 10. You're going to hear standard error of the mean, and that's just another way of saying standard deviation. So let's think about a quick example here. If the average IQ score is 100 with a standard deviation of 15, if we took a sample of size 9, what would be the mean and the standard deviation? So that's referring to thinking about just a general sample of size 9. The mean of those samples is going to be the same as the population, and the standard deviation of those samples is going to be the true standard deviation divided by the square root of the sample size. Generally speaking, this yields a pretty ugly decimal. Because these are nice numbers to work with, we know the square root of 9 is 3, so we get a nice clean 5 for the standard deviation. Normally, like I said, this is a big ugly decimal. Same idea if we took sample of size 25, what would be the mean and the standard deviation? We would still expect the mean to be around the true mean, 100, and the sample standard deviation would be 15 over the square root of 25 this time. Again, they use clean numbers in this example, so we would get 3. So remember that the mean stays the same, nothing changes there, but the standard deviation gets adjusted, and it's important to know how to adjust that standard deviation. Alright, so we said if the population distribution is approximately normal, then the sample distribution is approximately normal. So most population distributions are bell-shaped, and if they are already bell-shaped, then I know when I take samples, I'm going to get a bell-shaped curve. Let's look at this example 4, though. The following histogram represents the number of people living in a household in the United States. It is known to have a mean of 2.9 and a standard deviation of 1.48. Looking at this histogram, are these data approximately normal? Is this bell-shaped? So the majority of the data is here, and then it trails off as we get more and more people in the house. So that's not a nice symmetrical bell shape. That is skewed to the right. So no, these data are not approximately normal. They're pretty well skewed right. We see the majority of the households have between 1 and 3, maybe 4 people in them, but there's a few households that have more than 4 people in them. So we have skewed right. A computer simulator, I believe this is through StatCrunch, which is a software program for statistics. We don't get into it because we just don't have that kind of access. But there are statistical programs that can pull samples. So if this is our population, if we took 1,000 samples of size 4 and created a histogram of those sample averages, we get the output below. I know you can't read all the little numbers, but just glancing at this, you can see how nicely bell-shaped that is. And it's centered around, that's 2.8. And remember the mean was 2.9. So it centers right around 2.9, and you'll see the nice bell curve over it. So even though the population was skewed, when we pull samples, most of our samples are going to come from where the majority of the data are. We're not going to get very many samples up here. So what happens is the distribution becomes bell-shaped if we take enough samples. So we took 1,000 samples, and that was enough to make a nice bell curve. So this is called the central limit theorem. Regardless of the shape of the underlying population, so skewed, uniform, bell, it doesn't matter, the sampling distribution of X bar becomes approximately normal as their sample size increases. So even though we only took a sample of size 4, because we did it 1,000 times, that's what we're focusing on. Because we repeated this 1,000 times, that's what created this bell-shaped distribution. So this is the part you need to remember. In order to safely assume that the sample distribution will be approximately normal, we need a sample size of at least 30. That is our magic number. If our sample size is at least 30, we can say that the sampling distribution will be bell-shaped, even if we don't know the shape of the population. So let's look at a quick example of that. Number 16 at the bottom says, a simple random sample of size 36 is obtained from a population with a mean of 64 and a standard deviation of 18. Part A says, describe the sampling distribution. When we see that phrase, describe the sampling distribution, there are three features we want to look at. The first one is shape, the second one is center, and the third one is spread. So anytime it says describe the sampling distribution, we want to figure out the shape, the center, and the spread. For the shape, we're either looking for it to say that it's normally distributed in the problem, which it does not, or we're looking for that sample size to be at least 30. So because our sample size was 36, our shape is normal or bell-shaped, and that's because n is greater than or equal to 30. So as long as our sample size is at least 30, we can say that the distribution is normal or bell-shaped, even if it doesn't say so in the problem. The center never changes. The center is always the same as the population. So if the mean of the population is 64, the mean of all the samples will be around 64. And finally, the spread. The spread is the standard deviation of all the samples. And we're going to use the formula we have up here, the standard deviation of the population divided by the square root of the sample size. So that's 18 divided by the square root of the sample size. Now they keep giving us perfect square sample sizes. That will not always be the case. But for these first few examples, these are nice, clean numbers. Alright, so it's 18 over the square root of 36. Again, normally that yields an ugly decimal. This happens to be a clean 3. So our standard deviation for the population is 18. Standard deviation for the sample is 3. You might want to get yourself another sheet of paper to do parts B, C, and D so you have plenty of room. I try to save space, but sometimes that's not helpful. Alright, let's set up here. There we go. So for part B, it says, what is the probability that X bar will be less than 62.6? So because we said that the shape is normal, we can use normal CDF just like we did in chapter 7. So we're going to do normal CDF. Remember, we have a lower bound, an upper bound, a mean, and a standard deviation. Less than 62.6, if you think about the curve that we practiced drawing back in chapter 7, less than 62.6 will go from negative infinity to 62.6. Whether or not there's a line underneath the inequality does not change anything for continuous distributions. For discrete, back in chapter 6, it made a big difference, but for continuous, because those decimals can go on forever, it doesn't matter whether or not it has a line underneath it. So negative infinity to 62.6 represents less than 62.6. The mean is 64. And instead of using the population standard deviation, we're going to use the one we calculated, the adjusted standard deviation for a sample, which is 3. So normal CDF, practiced that a lot in chapter 7, negative infinity to 62.6 was 64 and 3. And that gives us 0.3204. So it's the same conclusion as chapter 7. There's a 32% chance that our sampling distribution will be less than 62.6. So same interpretation from chapter 7. Let's look at part C. What is the probability that X bar will be greater than or equal to 68.7? So again, because the shape is normally distributed, I can use normal CDF. Lower bound, upper bound, mean, and standard deviation. Because it's greater than 68.7, we're going to go 68.7 to infinity. The mean is still 64, and again, I'm going to use that adjusted standard deviation of 3 for the sampling distribution. So normal CDF, 68.7 to infinity. 64 with the standard deviation of 3 gives me 0.0586. And one last time for between. Part D, what is the probability that X bar is between 59.8 and 65.9? So normal CDF, 59.8, 65.9 with a mean of 64 and a standard deviation of 3. Normal CDF, 59.8, 65.9, 64, and 3. Gives us 0.65, that rounds to 60. So set up just like Chapter 7, the only difference here is that the standard deviation is the adjusted based on your sample size. So that's the part you need to remember. Everything else sets up the same as Chapter 7. All right, moving on. That's it for Section 8.1. I have a couple extra examples here just to kind of make sure this is sinking in, but it's a little repetitive because it's all from the same information from Chapter 7. So if you feel comfortable, you don't have to follow along with these last two examples, but I pulled them from the previous edition of the textbook just to give us some more examples. So this is number 24, but again, I don't think it's in the new textbook. I think it was in the old edition. So based on tests of a Chevrolet Cobalt, engineers have found that the miles per gallon in highway driving are normally distributed. So as soon as you see that word, you don't have to worry about the sample size. If it says normally distributed, you're good. With a mean of 32 miles per gallon and a standard deviation of 3.5 miles per gallon. First question says, what is the probability that A, randomly selected cobalt, gets more than 34 miles per gallon? This question's just like it was in Chapter 7. Notice no sample size is given, so it's just one car. So we're just going to do normal CDF. More than 34 miles per gallon will be 34 to infinity. The mean is 32. Now, in the standard deviation, we don't have to make any adjustments because it's just for one car. Dividing by the square root of 1 doesn't do anything. So we're going to do second bars, normal CDF. So if there's not a sample size, you don't have to make any adjustments. 2, 8, 3, 9. So again, that's just like Chapter 7. Part B gives us a sample size. It says that 10 cobalts are randomly selected, so N equals 10. And the miles per gallon for each are recorded. What is the probability that the mean miles per gallon for all 10 exceeds 34 miles per gallon? So normal CDF. Same setup, 34 to infinity, same average. The only difference is that 3.5 gets divided by the square root of 10. Now you can type it in just like that into the older or the newer calculators and it will do the math for you. So normal CDF, we can put in 34, 10 to the 99th power, mean of 32, and then you can do 3.5 divided by the square root of 10. The square root key is above the x squared key. You have to hit second and then x squared and you'll see the little square root. You don't have to close the parentheses, but you can, and it will crunch the number for you. On the older calculators, normal CDF, 34 to infinity, 32, and then all you have to do is 3.5 divided by the square root of 10. Again, you don't have to close the parentheses, but you can. You can close it for the square root and then close it for normal CDF. You'll get the same answer. So 0.035, that would round to 4. So notice for one car, it had a 28% chance of getting more than 34 miles per gallon. If I'm trying to get 10 cars to have more than 34 miles per gallon, that's harder to do. So there's only a 3.5% chance of that happening. And then the last part, 20 cobalts are randomly selected, and the miles per gallon for each car are recorded. And same questions, this time n equals 20. Normal CDF. So as the sample size increases, the bell curve gets tighter and tighter and tighter because that standard deviation is getting smaller. And so it's harder and harder to exceed a number either in the negative or positive direction because the tails of the curve are getting smaller. So the bigger we divide the standard deviation by, the bigger number here, the smaller the spread. And the smaller the spread, the less likely those extremes are going to happen. Alright, so 34, 10 to the 99th power, 32, and then I'm just going to type that in just like that, 3.5 divided by the square root of 20. Close the parentheses if you want to, and you get 0.0053. So less than 1% chance of happening. And the question says, is this result unusual? Remember, unusual is less than 5%. So yes, 0.005 is less than 0.05. So it is unusual. Again, if I'm trying to get 20 cars to have more than 34 miles per gallon, that's harder to do than just one car. So the bigger sample you have, the smaller those tails get. So the less likely you are to exceed a number bigger than the average. All right, I'm going to stop there so the video doesn't cut me off, and then I'll go ahead and pick up with that second example.